In this lesson, we'll continue our work on polynomial and rational inequalities. In particular, we'll do an example problem involving a rational inequality, that is, an inequality involving a quotient. The general procedure will be the same. So we'll start by getting everything on one side of our inequality. We'll then factor. We will then determine the values for which each factor is 0, and these will partition our real number line into intervals. We'll use a test value in each interval to determine the sign of each factor, and we'll use that to solve our inequality. So here we have the rational inequality, 1 plus x over 1 minus x less than or equal to 1. The first thing we'll do is bring that 1 to the left-hand side, so we get 1 plus x over 1 minus x minus 1 less than or equal to 0. And now we need to get a common denominator, so this 1 we're going to go ahead and write as 1 minus x over 1 minus x, because the denominator of our first fraction is 1 minus x. So when we do that, we get 1 plus x over 1 minus x minus 1 minus x over 1 minus x less than or equal to 0. Now the next thing we need to do is go ahead and combine these fractions. So they have a common denominator. Now, one thing I want you to watch out for is that when we combine these fractions, this negative sign means we're subtracting off the entire fraction. So our common denominator will be 1 minus x, but this negative sign will subtract off the entire numerator, 1 minus x. So we get 1 plus x minus the quantity 1 minus x all over our common denominator 1 minus x. Now let's simplify our numerator. So we get 1 minus 1, so that's 0. And then we get x minus minus x, which gives us a 2x in the numerator. So we get 2x over 1 minus x less than or equal to 0. Our fraction is now in fully factored form. There's nothing left to factor on the left-hand side, so we can go ahead and set up our sign chart. So what are the zeros of each factor? So 2x is equal to 0 when x is 0, and 1 minus x, our denominator, is 0 when x is 1. So these are the only values at which our expression could possibly change sign. So this partitions our real line into intervals, and now we'll just do a test value in each interval. So for x less than 0, I'll try x is negative 10. The numerator, 2x, would definitely be negative. 2 times something negative is negative, over 1 minus, say, negative 10 would be positive. So I get negative over positive, which is negative. This time our inequality is a less than or equal to, so I need to check my endpoints as well. So what about x is 0? When x is 0, I get 0 over 1, which is less than or equal to 0, so 0 will be included in our result. What about 0 to 1? I'll use the test value, let's say 1/2. 2 times a half would be a positive number. 1 minus a half is also a positive number, so I get positive over positive, which is positive. And now finally to the right of 1, so I'll do the test value, let's say 5. 2 times 5 would be positive. 1 minus 5 would be negative, so I get positive over negative, which is negative. What about our endpoint of this interval, x equals 1? Well, when we look at x equals 1, our original expression is not defined when x equals 1, so we will not include the endpoint x equals 1. So that means our final solution for this one, we want x less than or equal to 0, so we're including our endpoint of 0. So we get x less than or equal to 0, or x can be greater than 1. So remember, we wanted to know where our expression is less than or equal to 0, so x greater than 1. But again, we're not including the endpoint 1 because our expression is undefined when x is 1. So we found our solutions of this inequality. If we want to write this in interval notation, so less than or equal to 0, means minus infinity to 0. And now I'm going to use square brackets here to indicate that we are including the endpoint of 0, and then union x greater than 1, so x going from 1 to infinity. But notice here that I've used my open or my curved bracket because I'm not including the endpoint x equals 1. So when our inequality is a less than or equal to or greater than or equal to, we must also include, we must also check the endpoints of our interval. So in this example, we had a rational inequality or an inequality involving a quotient. And again, our general procedure was the same. We just had to get a common denominator to deal with our fraction. But the general procedure is always to factor, determine the values for which each factor is 0. These divide our real number line into intervals. The expression can only change sign at the endpoints of these intervals, so we do a test value within each interval to determine the sign of each factor and therefore the sign of the overall expression, which allows us to solve our inequality.